Welcome to the Network H2 webinar, Interim Findings from Hydrogen Research. My name is Dr. Andy Smallbone. I'm an Associate Professor at Durham. We've organised this event through the EPSRC Network Plus, Network for a Hydrogen Fuel Transportation, which is a series of webinars which is looking at different aspects of hydrogen research related to the transportation sector. And this week, we're going to welcome two speakers who will present their interim findings from small research projects we funded through the network. Now, because of the research nature of this research, we've asked each speaker to present for about 25 to 30 minutes, which is from Stathis Tingas, Dr. Stathis Tingas from Edinburgh, Napier University. So do you want to start to queue up? He'll be talking about the computational analysis of zero carbon hydrogen fueled thermal engine for heavy duty transport applications. Dr. Tingas received a first degree in aeronautical science from the Hellenic Air Force Academy in Greece in 2005 and an MSc and a PhD in mechanics from Technical University of Athens. And before his current appointment, he was an aircraft engineer with a specialty in jet engines and did a postdoctoral research associate at KAUST and is a lecturer in engineering at Perth College. And he's currently a lecturer in mathematics at Edinburgh, Napier University. So if you're ready, then we'd like to hear more about your project and your progress so far.
Yes, of course, Andrew. Thank you so much for the introduction. Well, good afternoon, everyone. My name is Stathis Tingas. I'm a lecturer in mathematics at Edinburgh, Napier University. And for the next 25 minutes, I will talk to you about the progress made on this project, which is a computational study about a novel zero-carbon hydrogen-fueled thermal engine for heavy-duty transport applications. A number of people have been involved in this work, therefore the proper credits should be given to all of them. So Professor Manos Paul is the current project's co-PI, and Michael Greencorn is working under his supervision. Professors Thanos Megaritis, Lionel Ganipa, and Nodas Masterakos from Brunel and Cambridge are the project's partners. And last but not least, the two undergraduate students, Iliana Dimitrova and Oliver Fernie, that have both been working under my supervision on different aspects of this project. So, in a nutshell, the objective of the current project is to perform a feasibility study using simplified numerical models of a new zero-carbon hydrogen-based technology that will allow the fast decarbonization of trucks and ships. I will firstly talk about the motivation of this work to allow me then to introduce a green ignition promoter. Then I will briefly highlight the aim of the individual objectives of this work. Next, I plan to dedicate most of the time discussing the results obtained so far. And at the end, I will also discuss the remaining elements of this work. So, as I already mentioned, the project focuses on heavy-duty transport applications like ships and trucks. But why? What's the problem there? Well, the decarbonization of these applications through electrification has not been very attractive so far. And there are many reasons for that. I'm not going to discuss them here, but there seems to be a consensus both among policymakers as well as the research community that there is no clear solution to their decarbonization. Yet, the UK government has set clear goals to this regard. Now, all trucks will need to be zero emission by 2040. And notice that this is a decade later than the 2030 ban of all new diesel and gasoline vehicles. With regard to ships, the aim is to reach net zero as early as feasible. At the same time, hydrogen has been identified as a key player in the decarbonization of our society, not only in the UK, but also globally. So one question can then naturally rise, which is, can we use hydrogen to decarbonize these heavy-duty transport applications? Well, there is the option of fuel cells, but they are typically quite expensive. So the industry is not very keen to buy in the idea. So ideally, we would like to have a technology relying on retrofitting. Now, both ships and trucks are predominantly powered with compression ignition engines. Okay, so can we just replace diesel fuel in these engines with hydrogen? Well, it's not that simple because hydrogen would simply wouldn't burn. Hydrogen has many unique features, and one of these unique features is that its very high autoignition temperature, which explains why it does not burn in conventional combustion ignition engines. Okay, so how can we tackle this? How can we basically burn hydrogen in compression ignition engines? Well, three strategies have been proposed so far. The literature for the first two is quite scarce. The last one is more popular, and you will see why. The first approach is to use very high compression ratios, above 30. High compression ratios mean that the in-cylinder temperature will be sufficiently high to enable the ignition of hydrogen. Now, compared to the typical range of 15 to 20 that conventional compression ignition engines currently operate, this basically means engine redesign, which is not cost-effective. The second approach is to use a glow plug. This glow plug will preheat the in-cylinder air or the in-cylinder charge. This is not actually a bad idea, but the preheating leads to decrease of the engine performance and in certain cases also to high NOx emissions. Now, the last approach is to use a small quantity of a second fuel, which is usually called a pilot fuel, which is more reactive than hydrogen in order to initiate the ignition. There are many benefits with this approach. One is the flexibility in operation, other is the increased efficiency, and many others. But so far, only carbon-based fuels have been proposed for use. In fact, most of the times, the pilot fuel was proposed to be diesel. Okay, so we are getting somewhere now. So if we were able to use a non-carbon-based fuel as an ignition promoter, then we would probably have cracked the problem. And ideally, if this ignition promoter is a substance already available in the market, so we wouldn't, in that case, we would have to set up a new logistics support totally from scratch. So is there any such substance? As a matter of fact, there is. It is hydrogen peroxide, and you can literally find it in any convenience store or supermarket in diluted form, diluted in water, basically. The idea of using hydrogen peroxide in combustion is not actually new. It dates back to the 40s, when it was first used as a rocket propellant and fuel for submarines. But apart from military and aerospace applications, where it is used even nowadays, in fact, it has also been used in transport-related applications. There, it has been used as an ignition promoter, just like we propose in the current project. So as you probably have realized by now, what we propose is the use of hydrogen and hydrogen peroxide blends to enable combustion in compression ignition mode. We also consider water dilution for two reasons. Firstly, because hydrogen peroxide would most probably need to be diluted in water anyway. And secondly, because water dilution is an established method for reducing NOx and mitigating abnormal combustion like NOx. Now, given the limited resources and time in the current project, we have been using simplified numerical models to explore the feasibility of the proposed method. Our investigation includes two branches: the homogeneous charge compression ignition mode, the Hcci mode, and conventional compression ignition mode. So basically, pre-mixed and non-premixed combustion modes. Due to the limited time, I will be discussing next the results from the Hcci mode, which is the work package that I have been leading, while the compression ignition mode is led by Professor Manos Paul. Our investigation focuses on engine performance characteristics, combustion phasing, and NOx under various conditions. We are also aiming to touch on the limitations of abnormal combustion as manifested by increased pressure rise rates and to provide some insight on the available injection strategies. I already mentioned that the model we have been using is fairly simple. It is a zero-dimensional single-zone Hcci model available in the ChemKing Pro suite, which solves the species and energy equations along with an additional equation for the volume change. The engine cylinder specifications, typical of a conventional compression ignition engine, are shown in the current table. One thing to note is that although we did investigate a range of compression ratios, in the following, I will only show results for the case of compression ratio equal to 17, since this is more relevant to the applications we are interested in. Another point to highlight is that the conventional definition of the equivalence ratio is no longer valid. So we have been using an effective equivalence ratio defined as shown in the current slide. I have organized the results in two sections. In the first, we only consider hydrogen and hydrogen peroxide blends, so no steam addition. These results have recently been published in the International Journal of Hydrogen Energy, so you can find more details there. For this case, I will start with a comparison against the glow plug approach, that is the preheating of the mixture. Then discuss the effect of hydrogen peroxide addition on the engine performance and close with the investigation under constant and low load conditions. The second section includes steam dilution as well. Unlike the first part, these results have not been published yet since we're currently working on the manuscript. Firstly, I will present a comparison against the glow plug approach, then discuss the effect of both hydrogen peroxide and steam addition on the engine performance, and close with the investigation under constant and high load condition. So let's start with the first part. Now, the investigation was performed in a range of equivalence ratios and engine loads. Each case of hydrogen peroxide addition is compared against the respective glow plug approach, which means we remove the hydrogen peroxide and properly increase the inlet temperature. Now, for a fair comparison, we ensure that the ignition occurs at exactly the same crank angle degrees between the two cases. For example, at phi equal to 0.1 and 1000 RPM, we used 12% hydrogen peroxide to achieve an ignition crank angle equal to 1.89 degrees. And in order to achieve the same outcome without any hydrogen peroxide, we had to increase the inlet temperature to 386 degrees. You can clearly see that when hydrogen peroxide is added, Imep, power, and torque all increase substantially. Thermal efficiency also increases, but not that much, and NOx emissions decrease significantly. Similarly, at phi equal to 0.2 and 2000 RPM, we had to use 10% of hydrogen peroxide to achieve ignition at 1.7 degrees. And in order to get the same outcome in terms of the ignition delay, without any hydrogen peroxide, we had to increase the inlet temperature at 390 Kelvin. The effect of hydrogen peroxide addition on the engine performance is very similar to what I described for the case of phi equal to 0.1 and 1000 RPM. That is, Imep, power, and torque increase all significantly, thermal efficiency slightly increases, and NOx reduce a lot. In summary, the comparison against the glow plug approach reveals that as the mixture becomes richer, firstly, the required hydrogen peroxide addition to achieve ignition at roughly 2 angle degrees decreases substantially. Secondly, Imep, power, and torque all increase significantly with the addition of hydrogen peroxide. But as the mixture becomes richer, their increase drops. On the other hand, hydrogen peroxide addition also affects thermal efficiency and NOx. But as the mixture becomes richer, its impact remains unaffected, in that thermal efficiency only slightly increases while NOx decrease substantially. The results already discussed provide us some insight as what to expect when we are investigating the incremental increase of the hydrogen peroxide content at the initial mixture. So in terms of the ignition crank angle degrees, the addition of hydrogen peroxide results initially in drastic reduction of the ignition CAD, and further addition has negligible effect on the ignition promotion. Therefore, the ignition CAD levels off. This profile becomes attenuated at very lean conditions, that is at phi equal to 0.1. And in fact, as the engine speed increases, the dependence of ignition CAD on the hydrogen peroxide becomes roughly linear. In essence, as the mixture becomes richer, and regardless the engine speed, the effect of hydrogen peroxide addition on the ignition promotion becomes more pronounced. Now, in terms of the Imep, the increase that hydrogen peroxide induces seems to be mostly linear. If we were to look at the gradients of these profiles as a measure to assess the sensitivity of Imep to the hydrogen peroxide addition, we would find out that as the mixture becomes richer, hydrogen peroxide addition results in stronger impact. So the gradients basically become steeper, but the rate of this change becomes smaller. What I mean is that the change of the gradient from phi equal to 0.1 to 0.2, this change is larger than the change from 0.2 to 0.3. And that is larger in turn than the change from phi equal to 0.3 to 0.4. Now, it is interesting now to compare the variation of the thermal efficiency against Imep for various engine speeds, while maintaining constant the effective equivalence ratio. The variation in the load is achieved by varying the percentage addition of hydrogen peroxide. Firstly, the maximum thermal efficiency for each case of equivalence ratio and engine speed does not coincide with the maximum Imep value. This is due to the enhanced ignition advancement that is achieved by the addition of hydrogen peroxide, which promotes the ignition occurrence to the angle degrees before the top dead center. In addition, at constant phi and low load loads, the engine speed appears to move the curve to the right. That is, the same efficiency is achieved by the same Imep difference between two speeds. This justifies why at constant phi, the same thermal efficiency is achieved at all the engine speeds. However, while the engine load is increased further beyond the threshold corresponding to the maximum thermal efficiency, and the thermal efficiency starts dropping at constant phi, there is great variation in the response of the thermal efficiency due to the engine speed. It is worth noting that the Imep and thermal efficiency values reported in our work are significantly higher than those reported in earlier works that achieved experimentally hydrogen use in Hcci mode with appropriate preheating of the charge. An important aspect in hydrogen-fueled engines that requires special attention is that of NOx emissions, which can become quite high, especially when compared with conventional fossil fuels. At sufficiently low effective equivalence ratios, that is phi equal to 0.1 or 0.2, NOx emissions are so low that would not require any after treatment, regardless the engine speed. And this is the result of the relatively low maximum temperatures reached. However, for higher equivalence ratios, NOx emissions increase rapidly and reach values which may necessitate after treatment or the use of additional strategies to combat the increased emissions, such as the use of water or exhaust gas recirculation, EGR. Now, in the last part of the analysis, we gradually increase the hydrogen peroxide content while also reducing the equivalence ratio in a manner that the load is maintained constant at 33.8 newtons meters. And we did that for a range of engine speeds. This section further corroborates the strong effect of hydrogen peroxide addition on the thermal efficiency, particularly at 2000 and 3000 RPM. In view of the thermal efficiency, the hydrogen peroxide addition has practical value for percentages equal or larger than 4% at 1000 RPM, 6% at 2000 RPM, and 8% at 3000 RPM. In addition, it is shown that NOx emissions are extremely low at all cases of hydrogen peroxide addition and engine speeds, which is attributed to the generally low maximum temperatures between 15 and 1700 Kelvin. These results highlight the potential of the proposed technology requiring no after-treatment for the NOx emissions at low loads. So we covered the first section of the analysis. Let's now add steam dilution into the system to see how this would work. Now, similar to the earlier scenario, we compare our approach against that of a glow plug in terms of performance and NOx. So for each case of hydrogen peroxide addition, we ran another without any hydrogen peroxide, but having properly increased the inlet temperature to achieve the same ignition CAD. Now, unlike the previous scenario, we are now considering steam dilution. So, for instance, at phi equal to 0.5, 3000 RPM, and 10% of water dilution, we need 7.3 hydrogen peroxide to achieve ignition at 5 degrees. But if we remove the hydrogen peroxide, we would need to increase the inlet temperature at 393 Kelvin to achieve the same ignition delay time. You can clearly see that with our approach, that is, with the addition of hydrogen peroxide, Imep and torque increase significantly and NOx production decreases greatly. 3 points I would like to make here. Firstly, NOx decrease significantly with the addition of hydrogen peroxide, in agreement with what we found in the case of no steam dilution. And this reduction is associated with a decrease of the maximum temperature. Secondly, Imep torque and power exhibit considerable increase with the addition of hydrogen peroxide. And what is interesting is that this increase is favored with the increase of either the steam dilution or the equivalence ratio. Finally, thermal efficiency increases slightly with hydrogen peroxide, just as we showed earlier. Now, staying a little further on the comparison against the glow plug approach, what we did next was to first consider heat losses, and secondly, to keep fixed the hydrogen peroxide content at 5% and add incrementally steam dilution into the system from 0 to 10%. Then we removed the hydrogen peroxide and tried to replicate the same load output by properly increasing the inlet temperature, and the result in terms of Imep and torque is shown in the figure on the left. In most cases, increasing the inlet temperature was not sufficient, so we also properly increased the equivalence ratio additionally, and this is shown in the figure in the middle. For instance, to achieve an Imep value of 7.4 with 6% of steam dilution, with hydrogen peroxide, we achieved that by adding 5% at phi equal to 0.4. But with the glow plug approach, we had to increase the inlet temperature to 376 Kelvin, that is 56 Kelvin more, and the equivalence ratio to 0.535, which is a 34% increase. Now, the figure on the right compares the two approaches in view of thermal efficiency and NOx emissions. And the benefits of the use of hydrogen peroxide are showcased again. In fact, as steam dilution increases, the decrease in NOx increases and reaches 2 orders of magnitude difference. What is also very interesting is that thermal efficiency is also significantly affected. And the difference between the two approaches becomes more pronounced, mainly because of the increase of the fuel mass in the case where no hydrogen peroxide is used. Next, we consider the effect of both hydrogen peroxide addition and steam dilution on Imep and NOx emissions. The x-axis represents the hydrogen peroxide addition, and the y-axis denotes the steam dilution. Red color is for low values, purple for high values. We are obviously interested in the areas where NOx are low, that is red color, and Imep is high, that is purple. Generally, both Imep and NOx increase with the addition of hydrogen peroxide and decrease with the steam dilution increase. So at 1000 RPM, where phi is equal to 0.3, we can see basically that NOx are low for all conditions except perhaps for hydrogen peroxide higher than 15% and steam dilution less than 3%. So an Imep of 6 bars can very well be reached with 10% hydrogen peroxide and 5% steam dilution while maintaining NOx extremely low. At 2000 RPM and phi equal 0.4, an Imep of 10 bars can very well be obtained with just 10% hydrogen peroxide and 5% steam dilution, while again keeping NOx very low at around 100 ppm. These results showcase that steam dilution can indeed be an effective tool of reducing significantly NOx emissions, while also achieving good load outcomes with no more than 10% of hydrogen peroxide. Now, similarly to the scenario of no steam dilution, in the last part of the investigation, we incrementally increased the initially introduced steam dilution, but in order to maintain the torque constant at 65 newtons meters, we also increased the initial hydrogen peroxide. At first glance, we can see that at phi equal to 0.4, the hydrogen peroxide must be more than 30%, which is not very convenient because we would like to keep it lower than roughly 15 to 20%. At phi equals 0.5, we can indeed achieve the desired load outcome with low hydrogen peroxide percentage, but we would also need to increase sufficiently the steam dilution to avoid high NOx. But then the required hydrogen peroxide would have to increase to more than 20%. On the other hand, at an equivalence ratio of 0.6, we can achieve the desired load output with hydrogen peroxide being less than 10%. But NOx drops substantially only when steam dilution is sufficiently increased to 15 to 20%. All these preliminary findings reached through this investigation reveal that the proposed approach seems to be very promising since, firstly, it is clearly advantageous against the glow plug approach and the preheating of the charge. Secondly, the addition of hydrogen peroxide results in the increase of Imep and torque while also greatly decreasing NOx emissions. Thirdly, steam dilution could be an invaluable tool offering unique operational flexibility since it can reduce tremendously the NOx emissions. That, in combination with a balancing of the equivalence ratio, can require less than 10% of hydrogen peroxide, regardless the operational requirements. So what is left to be done in this project? Well, the work led by Professor Manos Paul is still in progress since it only started last month due to bureaucracy. Hence, its completion has been extended to late June. That would be a very interesting part because it will focus on the conventional compression ignition engine mode. As for my part, there is one thing currently in progress, expected to be completed next month, and that is the limitations introduced due to the pressure rise rate and the combustion efficiency. And with that, I would like to thank our funders, the Hydrogen Network, for their financial support to perform this work. Thank you very much.